Alrighty, you guys. So today we are going to talk about something called a piecewise function. Up here with me, Steve. Piecewise functions. Have you ever seen a function that looks something like this? You ever seen a piecewise function? Okay. They look something like f of x equals, and then usually there's one of these sort of curly brackets. And then there's a couple different things that we have as options, a couple different essentially functions to choose from. And we choose the piece, that's why they're called piecewise functions. We choose the piece of our function that's appropriate based on the domain, based on the x values that we're looking at. So the idea is for a piecewise function, I maybe have a function that isn't predictable with just one function. I can't describe it, I should say. I can't describe everything that happens with just one function. I've got a section that maybe behaves like a line, and maybe a section that behaves like absolute value, and maybe a section that behaves like a parabola. Maybe I've got a section that behaves like an exponential function. Maybe I've got like completely unique things that happen, completely unique y values that I'll get based on my input, based on my domain. Okay, so that's what we use piecewise functions for. We describe functions. We use them to describe functions whose behavior is different based on the domain. Okay, so for different values of x, we see different things happening. So the first example that I want to talk about really quickly, just sort of an intro, something that you guys have probably seen at some point. If you've been somewhere and they give like an admission fee, but then they say for groups of 10 or more, or for groups of 12 or more, there's a different admission fee. Has anybody ever seen something like that? Zoo, movie theater, amusement park, something like that, where if you come in a group, you get a little bit of a discount. That we could model with a piecewise function. So for this first example, a museum charges $5 per person for a guided tour, or a fixed fee of $50 if your group is 10 or more. So for my first option, it would be $5 per person if my domain is somewhere between 1 and 9. So if my number of people is between 1 and 9. If I've got 10 or more, so if my domain is greater than or equal to 10, then it is a flat fee of $50 for that group. So different things happen based on our domain. In this particular example, we have different prices based on how many people we bring. So this idea, we're identifying what happens based on the domain, okay? We've got a little bit different function to describe what happens based on the domain. That's the whole idea of a piecewise function. So this is a piecewise function that has two pieces. If we take a look at the graphs that we have down here, we're looking at piecewise function graphs that have two pieces, it looks like, for each of these. I've got a section here and a section here, here and here, here and here. Most of these have two pieces. If we look at this last example, I've got 1, 2, 3 pieces there. Okay. Piecewise functions can have as few as 2 pieces, as many pieces as you want, or as it takes to describe what's happening. Okay. So for example 2, we're going to identify our domains here, and we're actually going to go ahead and write these piecewise functions that describe what's going on. We've got, for the most part, a lot of linear functions. So these shouldn't be too bad. For the ones that are non-linear, I'll guide you through those. We might be a little rusty on how to write maybe a root function or something like that. But for our first example, okay, my domain split occurs at 1. Do we see that? How 1 is that x value where different things start happening. Okay. I can have piecewise functions that meet up. So I might have a piecewise function where I've got this, and then at that same spot, maybe I take over and those y values happen to match. That doesn't always happen, as we can see from our examples here. Those y values aren't always going to match for those piecewise functions. That's okay. So for my first piece, right, I'm going to write a function for this guy. For my first piece, we're going to start here with the lower domain values. So since I've got an arrow, that means I'm looking at everything from -infinity up to 1. I want to describe what's happening here. We've got a line, I can see the y-intercept, so I'm going to write slope-intercept form. My y-intercept is at -1, and my slope is, looks like up 2, forward 1, so 2. So my first piece of my piecewise function can be described by the line 2x minus 1. And this is true for all x values that are less than 1. Since we have an open circle here for this first part, strictly less than, not equal to. Open circle means not equal to, and strictly less than 1. For the second part of our piecewise function here, I've got another line. Again, we're looking at domain values that are 1 or greater, so 1 to infinity, but we're going to include 1 this time. But this time we didn't. Okay, we're including 1 in the second piece. I've got a line. My slope is 1. If I wanted to, I could trace this back to what its y-intercept would be to write slope-intercept form, or we could do point slope from a point on the graph. Doesn't matter to me. This is the point 2 comma 3. So that would be 1 times x minus 2 plus 3. If you really want slope-intercept to be consistent, this would be x minus 2 plus 3, which is x plus 1. So the other piece of my function is represented by the line x plus 1. And I apply that for all parts of my function where the domain is greater than or equal to 1. Because this is a filled in circle there, that's an or equal to. We include 1 with this second part of our function. What questions do you have for me so far? Feeling okay about this? Okay, let's do another one. Our next graph here, the lower part of our domain is for x values that are what? X values that are less than 0. Give me 1 second. Hello, Ms. Fuji. Oh, should he bring, or should they bring things? Okay. Riley, they need you down in the office. Ms. Foster said make sure you bring your stuff. Okay, sorry about that, guys. Okay, so you can remind me what you said, domain values that are x is less than 0. Why not or equal to? Why not equal to 0? Yeah, open circle, okay? Strictly less than. So how could I describe this piece of my function? What's happening there? It's a straight line, right? More specifically, it's a horizontal line, right? So this is going to be one of those y equals lines. What's y equal to? 3. This is a y equals 3 line. So as I go to write my piecewise function, which I'll do kind of up here, f of x equals just 3, right? F of x equals 3 when x is less than 0. And then my other piece down here, can we agree that that is not a line? That is not a linear function. It's got a curve to it. Yeah. This looks like a root function, and it's a little distorted because our x-axis, the ticks are by a half, right? Where the y-axis, the ticks are by 1. So a little distorted, but this looks like the square root of x to me. So we describe our function as the square root of x for domain values that are, what kind of x values would we use this other part for? Greater than or equal to 0, right? It's filled in circle there. So when x is greater than or equal to 0. Not too bad so far? Okay. Let's take a look at our next example. For the lower part of our domain here, see that V shape? Absolute value. I guess if I really wanted to, I could break this one into 3 pieces and describe this section and then describe this section and then describe this final section. But I can describe that with an absolute value function altogether. So that's what I'm going to choose to do here. So f of x equals. This is absolute value, centered at 0. The sort of slope of my sides is just 1. So this guy would just be the absolute value of x. What's the domain for the absolute value portion of my piecewise function? X goes from where to where? X is less than 2. Any x values less than 2 fit into that portion. And then for the later portion of my function, what's happening there? Just looks a little familiar. We just did something pretty similar in the last problem. Go ahead. Yeah, horizontal line. We describe those as y equals line, y equals 1. So this would just be 1 for x values that are greater than or equal to 2. Very good. Our last piecewise function here is in 3 distinct pieces. So we're going to use 3 distinct functions to be able to describe it. My earliest part of my domain, my lowest part of my domain, I should say, is sort of parabolic in nature. This is just the function x squared, right? Vertex at 0, 0. My sort of rate of change for the vertex to the next point is out 1 and up 1. So this is just x squared. So as I write my function here, I've got x squared. That's my function when my domain is somebody I haven't heard from yet today. What's the cutoff on the domain for this one?
X is
less than or equal to 1. Okay. Build in circle or equal to. So x is less than or equal to 1. And now the next piece of my domain, the next part right here, another horizontal line. Okay. We're equal to what there for that middle piece? Y would be equal to 3. And this one's a little tricky because it's not just x is less than or x is greater than, but x is defined between 2 values, right? I've got to specify those 2 values. So from 1 up to and including, since we've got a filled in circle there, 2. Does that make sense? X has got to be between 1 and 2. We include 2 with that or equal to. And then for my last portion here, another line. My slope would be 1. We could write point slope if we wanted, or we could follow it back to what our y-intercept would be, which would be 0. So 1x plus 0, or just 1x. So the last part of our function would be x. And for domain values that are greater than 2, x is greater than 2. So we've looked at piecewise graphs. We've written functions to describe piecewise graphs, making sure we pay attention to what domain fits each piece. The next thing I want to look at is evaluating with piecewise functions. We talked about evaluating at the beginning of this unit. We're continuing to see evaluating as our sort of common theme running through. So we're going to look at how to evaluate when I've got a piecewise function. When you don't have a piecewise function, whatever that x value is, you just plop in for x, right? Because that's your only choice. But when we have a piecewise function and we're evaluating, I need to pay attention to those different domains that are described for each piece. And I need to make sure I'm plugging in my x, evaluating for my x over the appropriate piece of my function. So I'm going to evaluate, we'll start with 46. I'm going to evaluate f of -3, f of -2, f of -1, and f of 0. So when I evaluate at -3, I need to make sure I'm evaluating in the correct piece. So this top piece is for x values that are less than -2. The bottom piece is for x values that are greater than or equal to -2. So am I, for -3, going to use the top piece or the bottom piece? The top piece, right? I need to pick the one that is, right, appropriate for my x value. -3 is less than -2. So this would be -3 plus 1. So -2. The actual evaluating part isn't that difficult. The tricky part here is making sure that I'm evaluating in the correct place. How about f of -2? Am I using the top or the bottom piece here? Yes. Pay attention to your, pay attention to your domains that are described here, or equal to, I'm going to plug into the part that is equal to -2. So -2 times -2 minus 3. That would be 4 minus 3, which is 1. How about f of -1? The bottom, -2 times -1 minus 3. That would be 2 minus 3, the -1 there. And then how about f of 0? The bottom one again. Now, is it possible, I'm going to kind of come back to this conversation really quickly. Is it possible that I will see piecewise functions where I could not plug in a particular value? Sure. If I have a piecewise function, I'm going to flip back to my graph here to scribble on one of them for just a second. You guys can say where you're at. But if I had a piecewise function where maybe, let's say this guy didn't start at 2, but it started at 3, I wouldn't be able to evaluate f of 2. I wouldn't be able to evaluate f of 2.1 or f of 2.5 or f of 2.999. If I didn't start my domain for this second part until 3, and there was nothing in here, right? No function to describe this, that means that I've got something that's, well, we already have something that's not continuous, but it would mean my domain isn't continuous. And that'll happen sometimes. That's okay. But do pay careful attention to the greater than, less than, and in particular the or equal to piece. Okay. So for the next problem, same idea. This one should go really fast. F of -3. Is that the top piece or the bottom piece? The top, or equal to -3 means it's got to be the top. The reason this one's going to go fast is because these are horizontal lines that we're looking at here. It's either at 1 or it's at 0 for that function value. How about f of -2? Less than or equal to or greater than. -2 is greater than -3, so that would be 0. How about f of -1? The bottom one to be 0 again, and then have what's f of 0? What would it be? It'd be 0 again, right? Because 0 is greater than -3. Not too bad. We'll do one more together. So for 48, we want to find f of -3. Which piece will I look at, the top piece or the bottom piece? The top piece. -3 is less than or equal to -1. This would be -2 times -3 squared plus 3. That would be 9. -18 plus 3 would be -15. And then f of -2. Top or bottom? Top again. So this is -2 times -2 squared plus 3. -2 squared would be 4. Multiplied by 2, we get -8 plus 3 would be -5. For f of -1, top or bottom? Top again, because that's the section that includes -1. -2 times -1 squared plus 3. This would be 1. So -2 plus 3 is 1. And then finally, f of 0 here. This one goes into the bottom. Greater than -1. So 5 times 0 minus 7. That's 0 minus 7. So -7. Not too terrible? Okay. I would like you now to try 49, 50, and 51. Okay. Take a couple minutes, try those on your own. And then when I tell you I'd like you to compare your work with a neighbor. Okay, and that's where we'll end in our notes packet for today.